So we're going to explore this idea of transformations of functions in this lesson. And you're probably already familiar with this idea from Algebra 2. The goal here is to get really familiar with this function notation, f of x notation, and how transformations look in this notation. Okay? So if you're not sure what I mean by transformation, let me just remind you what we're talking about, because you actually do know for sure. So here we have a linear function that is your wage. So this would be something like this to start. And notice my y-intercept is negative because of this minus 100. In the context of this problem, I'm guessing if we're talking about taxes, I'm guessing that minus 100 is your tax, right? Well, a $50 tax cut, if f of x is how much money you're making and x is how many hours you work, that means you have 50 more dollars for every value of x. So no matter how many hours you work, you're getting $50 back. So what that would look like would be a vertical shift, right? That's probably a little too high. And what that would look like algebraically would be we would have f of x plus 50. We added 50 to the function, and that would be equal to 13x minus 100 plus 50, which really is equal to 13x minus 50 now. So the government's still taking a little bit of money, but less money than before. So in our function notation, my original function is f of x. My new function, my vertical shift, is f of x plus 50. And that is a transformation, and that's an idea you're definitely familiar with. It's not so bad, right? Next, we're going to consider a parabola. So notice we have a x squared, and we're just going to shift it around. So here we have translated left 5 and down 2. So we got to draw our original parabola, and then we'll figure out what our new parabola should look like. This is vertex form. This should be, again, familiar from Algebra 2. And vertex form is this. So writing parabolas this way means it has its vertex, its top or its bottom, at the point h comma k. And this is kind of familiar from our work on circles too. So h comma k in this case, we have 2, 4. So my vertex would be positive 2, negative 4. So only my x changes signs. And that's about here. And I'm just going to sketch a parabola. It doesn't have to be exactly what it would look like. Positive 2, negative 4. Okay. Left 5 down 2. Left 5 down 2. Well, left 5 down 2 would be my new vertex. If my old vertex was 2 comma negative 4, left 5 would be 2 minus 5, which is negative 3. And then down 2 would be down another 2, which would be negative 6, right? So what I did there, right, is I did plus minus 5, and I did minus 2. Okay, so negative 3 comma negative 6 would be, I don't know, down here somewhere, and that is a transformation. Okay, so this was f of x, my blue curve, and then my new curve, so g of x would be x plus 3 squared minus 6. So that's my new curve in orange there. Now, notice what happened here for my horizontal shift. So even though I subtracted 5 from my vertex, I added 5 in my actual equation, right? So this negative 3 was negative 2 plus 5, and that's my left shift. Okay, so this rule is tricky, and you can memorize this, or you can connect it to this idea of a vertex of a parabola, but make sure you write this down very, very clearly in your notes so we don't get it backwards. So a rightward shift of b units of f of x is taking f of x and transforming it to f of x minus b. And this is the opposite of what we would expect, right? Because that rightward shift, we'd expect it to be a plus. And then leftward shift is opposite. So if we're shifting a units, we're adding a inside of that parentheses. Okay. Vertical shifts are easy because it works how you would expect it to. So an upward shift is adding, a downward shift is subtracting. And notice the direction, vertical versus horizontal, that we're translating a function determines whether we're working inside or outside of the parentheses. Okay, so that's why this outside number for g of x changed the vertical coordinate of the vertex, and the inside number changed the horizontal coordinate. All right, now we're going to consider a different type of transformation, which is a reflection. Before we do that, I would make sure your notes are complete for our translations. We have two more families of transformations to consider. So I'm going to sketch a little coordinate plane here, and we're just going to sketch and label. And the way we're going to explore this is just using our graphing calculator, and this would be a great time to practice this a little bit. Do this along with me if you have your calculator handy. So we're doing square root of x, so I hit second and then x squared to get that square root sign, and then x. And we're just going to see what the graph looks like. And it's a sideways parabola, 1/2 of a sideways parabola. So just draw that sketch. It doesn't have to be super precise. And that sketch is h of x. And then we're going to switch colors. H of negative x, well, what would that mean? If I go h of x was square root of x, h of negative x would be square root of negative x. And then we're going to graph. And notice that is a kind of a flip of the function, so it now points the other way. So we call that reflecting across the y-axis. And then my last function, if I graph it, square root of, just kidding, the negative h of x, the negative is now on the outside. So negative square root of x. And when I graph that, notice that is a downward shift. So reflection across the x-axis. Okay. So those are reflections. That is pretty easy and intuitive. So what a reflection is, right, is a flip of the graph across the x or y axis. If you take more advanced math, eventually you'll study other reflections as well. But these are the ones we're worried about right now. So we have a horizontal reflection here for h of negative x, and negative h of x is a vertical reflection. So that's pretty easy, and I think works exactly how I might expect it to work if I didn't know what I was talking about. Okay, for our last trick, we're going to consider what is called a dilation, and a dilation is a stretch of a function. So take a second to read this problem if you haven't already. I'm not going to read it to you. Essentially what we're saying is we're using a sine function to model the number of kids in the hallway, which as you know, increases or decreases throughout the course of the period, right? So a sine function is this wavy function, right? And notice part of this is negative, so this doesn't make a whole lot of sense, and the actual function is actually more complicated than what I put here. But that's not what I want to focus on right now. So say we have this wavy function, and here we're going to kind of consider why these, like how a transformation might be useful in real life, right? And we're going to do this graphically, and I chose to use Desmos, just so you can see it clearly in the video, but also you could do this just as easily on your graphing calculator. So I'm going to sketch a graph, and this doesn't have to be necessarily accurate or have a scale at all, but I'm just going to sketch kind of a wavy graph. And let's see what g of 2x would look like. G of 2x would be, instead of sine of x, sine of 2x. And if I graph that, notice my waves get narrower, right? So that's a horizontal transformation. So here's sine of 2x, here's sine of x. So essentially I start in the same spot, but I have twice as many waves. And I'm, again, just kind of sketching sort of a random graph. We don't really need it to be precise for our purposes here. We're just exploring this idea, okay? So narrower waves. 2g of x, well, that would be 2 sine of x. And then, again, here is my original sine of x function, and when I put that 2 in front, notice my waves get twice as big, right? So here's 2 sine of x. So again, we're going to just draw a rough sketch here. 2 sine of x should be the same number of waves, but they're taller. So this is 2g of x. Okay. So to go back to the question, if we're doubling every student's number of hall passes, right, we would expect that the waves would be bigger, more students would be in the hallway at a time, right? So I would say that 2g of x is the better model in this case. And let's just capture the rule. So k times g of x was a vertical stretch, and g of k times x was a horizontal stretch in this case. So that's it. Those are our three families of transformations.